All right, so today we'll talk about wind energy. Okay, so we've seen this before. By the way, so this I couldn't find the one that works. Anyway, so here's how a lot of the electricity currently is produced. Okay, so you have two magnets here. This is a generator, and all you need to do is turn this piece of wire in between the magnets. Okay, now it takes a force to turn this thing. It won't, it's, it takes a force to turn this thing. Okay, so the energy that you're putting in is getting converted to electricity using this device. Okay, and we have various technologies. So this is at the heart of a lot of things. So in a dam, the flowing water is turning this thing. In a coal power plant, you burn coal. From the heat, you boil water, produce steam. The steam is turning this thing in a turbine. Okay. In a nuclear power plant, you split atoms, you split nuclei, heat is generated. Again, you boil water, and the steam is turning this. Okay. In a geothermal power plant, what is a geothermal power plant? It's extracting heat from deep underneath the ground. Okay, it gets warmer as you go underneath. So you have to go 2 kilometers. 2 kilometers is from here to Bethune-Cookman College. That's how deep you have to go in the earth. All right, you extract heat, again turn steam and all. Now today what we're doing is we're studying windmill. The wind is turning the blades of a windmill, which is turning this thing. And we're producing electricity. Okay. All right, so that's what we're studying today. So wind energy. Okay. So here's a pretty amazing thing. We've been harnessing wind for motion, so that's what sail ships do. And look at this. This sail ship can produce 8 megawatts of power. That is 1,100 horsepower. Okay, that is a small car will produce about 100 horsepower, 110 horsepower. So this is producing 100 times the power of a small car. Okay. So we've been harnessing this. In addition, wind energy has been used for grinding grain. So here's a place where you grind grain, and pumping water. So we've been harnessing wind energy for thousands of years. Okay. Look at this. What does this graph tell you? So to run the world, currently we use 16 terawatts. If you remember, 1 terawatt is 10 to the power 12 watts. Okay, and 1 gigawatt is 10 to the 9 watts. What is a gigawatt? Hoover Dam. Okay, so to run the world, all you need is 16,000 Hoover Dams. Okay, and you see, you could run the world just on wind. Okay, so there is enough wind energy to just run the world on wind. Okay, and wind and solar are the cheapest sources of energy production. Okay, so wind is going to play a big role in our energy mix in the future. All right, so as can be seen, only 16 terawatts is needed to run the world. There's enough energy to meet our needs on wind alone. Okay, so just wind alone can run the world. Okay. So there's a group at Stanford that has done studies, and they say by 2050, the world can be run just on wind and solar. The world can get 40% of its energy from wind and 60% from solar with existing technologies. Okay, so in the future, what do you think might happen? Solar cell efficiencies will increase. Okay.
There might be more of an increase because lately the gas prices and stuff.
Yeah.
We're gonna start putting more of like electric cars into them.
Yeah. So, But with AI, our power needs are going to increase. So, and a lot of the AI companies, what they're doing is they're getting their energy. They're planning to get their energy from nuclear reactors. Okay. So, anyway, what is the reasoning behind all those things? What is the main goal? You want to get all your energy without dumping CO2 in the atmosphere. Okay. So you want green sources. Okay, so here's this is this is before AI. Okay, if so, this is the current mixture. 80% of our energy is coming from fossil fuels and 20% renewable. And if you use the same mixture, and this is again before AI, at 2050, with the same mixture, you would need 20,000 Hoover dams to run the world. Okay, but if you, as we're switching to renewable, okay, to run the world, this was pre-AI. By 2050, all you would need is 12,000 Hoover dams to run the world. Why this discrepancy? Okay, so if let's make sure we understand this. So if you run the world with the current mixture of 80% fossil fuels and 20% renewables, if you went this, if this you evolve the same way, you need 20,000 Hoover dams to run the world. But if you switch to renewables, you need only 12,000 Hoover dams. The thing is, when you use fossil fuels, you're burning stuff, and from the heat, you're producing electricity. And when you're producing heat from electricity from heat, only 33% of that is converted to electricity. 65% is dumped out in the atmosphere. But if you're producing electricity directly from these renewable sources, you're producing electricity because with electricity, electric motors are very efficient. Okay? So with renewables, you can run the world on a lot less power. Okay? Look at this, the cost of renewable sources. Okay. Cost per megawatt hour. Okay, so this is, you guys ever see your electricity bill? So check this out next time. 1 kilowatt hour. Okay, so the cost of this on your electricity bill is about 12 cents. Okay, and it costs the electric company about 5 cents to produce it. So to run this much energy, for this much energy. Okay, what you can do with this thing is, so 1 kilowatt is 1,000 watts, so 100 watts times 10 hours. So you can keep a 100-watt bulb lit for 10 hours with 12 cents. That's what you can do. Okay. Or you can run, your refrigerator is about 500 watts. Okay, so you can run your refrigerator for about 2 hours with 10 cents. That's what you can do. This is a megawatt hour. Okay, this is a kilowatt hour. So this is 1,000 megawatt hour. 1,000 kilowatt hour. Okay. Okay. So the retail price of this should be 1,000 times this. 1,000 times this is $120. So the retail price should be $120. Okay. With 1 megawatt hour, you can run 1,000 homes roughly for an hour. Okay. Look at that. The cost to produce that. This is the retail price. The cost to produce that. This is $50. That's about $30, $40. Okay. So wind and solar are the cheapest. Then natural gas, but natural gas now is more expensive. what is the good thing about this? This price doesn't change. I mean, all it'll do is it'll get lower. This price fluctuates now with war and all. You see that fossil fuel prices are fluctuating. You don't know what the prices are going to be 10, 20 years from now. You know that what the price is going to be 10, 20 years from now for this guy. It's only going to get better. So if you want to invest your money, where are you going to invest, you know? And again, this is also good for the environment. Geothermal energy, and this is all the other costs. Okay. Gas peaker, this is expensive because you're running this only in times of peak demand. Okay, so you guys remember that our energy needs are like this. So during the time of the day, power, okay, it goes like this. So a peaker gas station is it's turned on only when you need high power during around noon and stuff like that. So here's this $5 billion company working only a few hours a day, and so the production cost is high. Again, you have to shut it down during all these times. All these times you have to shut it. You have to keep it shut. So that's what that is. Okay. All right, so again, wind and solar are the cheapest. Okay. Global installed wind capacity, and this is a slightly old information. How many Hoover dams do you need to run the world?
16,000.
16,000. By the way, there's in the U.S. we have about 1,000 Hoover dams installed. That's how many gigawatts of electricity we produce. Okay. So this is the wind capacity installed in the world. Okay, this is in gigawatts, gigawatts of electricity that's produced. Okay, so cumulative capacity, again, this is 650 gigawatts, meaning about 650 Hoover dams worth of is installed. Now it's about closer to 1,000. Okay, so out of every 1/16 of the power installed is coming from wind. Okay. But we want to increase that to 40% in the future. So we have a ways to go. More than 60,000 utility scale wind turbines are installed in the US, okay, with a cumulative capacity of 120 gigawatts. So we already have 120 Hoover dams worth of wind capacity installed. Yeah. Global wind capacity increased by 14% annually for this 10-year period. Every year it was increasing by 14%. Again, why are people putting money there? Fuel costs are zero, and it's the cheapest way of getting electricity. Wind power per capita. All right, so here's how you think about it. In the US, we consume the most power per capita, but this will give you a sense. Okay, do you guys, well, how much power is needed to run your house? About 1,000 watts or 1,500 watts. Okay, and let's say in your house 3 people are living on the average. Okay, so to run your life, you need about 500 to 700 watts. Okay, so this is and in other countries it's less. But so wind power per capita, how much power are you producing per person? Okay, so look at this. Denmark is producing about 800 watts per person. So Denmark is running, every Danish person is running their life just on wind power. That's what that means. Okay. In the US, we are producing about 200 watts per person. Okay. So just for your home needs, uh, that's the power produced. But there's other energy uses that you use for your. This doesn't account for your cars and all the stuff that you buy. There's energy needs for all of that. Okay, so much of Denmark's wind capacity is from offshore wind farms. Um, okay, do you guys know what might be the advantage of offshore wind farms?
Almost constant window.
A constant and stronger wind. Okay, so that's the advantage.
But isn't it also more expensive because it has needs a lot of maintenance?
Yeah, it's more expensive, but
The profit.
yeah, you're always doing cost benefit analysis. You're willing to spend more if, I mean, you wouldn't put that if you would make less profit. So, yeah. Wind turbines extract energy from wind by slowing it down. Okay, so what's happening is the following. So here's the wind blowing. Let's say it's blowing at 15 miles an hour, and it rotates the blades, and so it loses some of its energy because it spent that energy in rotating this wind blade. Okay, so if it's blowing at 15 miles an hour, after it goes through the windmill, now it's blowing at 10 miles an hour. And that kinetic energy got converted to the motion of the blades. And then what did the blades do? They turned this piece of wire between the magnets to produce electricity. Okay. However, so wind turbines extract energy from wind by slowing it down. However, they cannot extract all the available energy. They cannot extract because you can't stop the wind. To extract all the energy, you would have to stop the wind there, downstream. Okay. The maximum amount of energy that can be extracted is about 60%. Okay, so you can extract 60%, that's the upper limit. In practice, you extract about 40%. Okay? So the upper limit is given by the Betz limit. This is called the Betz limit. Okay? Actual wind turbines more commonly have efficiencies of about 40%. Okay? But that's good, you're just picking up money laying on the ground, and without a carbon footprint. Okay, efficiencies vary with the tip speed ratio. Okay, we'll come to the tip speed ratio. The ratio of the speed of the blade tip to the speed of the wind. So the tip speed ratio is how fast the tip of the blade is rotating to the wind speed. Okay, so let's say if the tip speed is going at 50 miles an hour and the wind is going at 10 miles an hour, so the tip speed ratio would be 5. Okay. Power in wind is proportional to the cube of the wind velocity. Okay. So so let's make sure we understand this. Power, the energy that you can extract, is proportional to wind velocity cube. So if the wind velocity doubles, 2 cube is 8. The power available is 8 times as great. Okay, so that's where our comment about offshore winds come. Offshore, if the wind velocity is twice as much, you're getting 8 times the power. So we are willing to, and so if the cost of an offshore windmill is twice as much, and you're getting 8 times the power, would you not do that? Of course you do. Okay. So this is very important. Power in wind is proportional to the cube of the wind velocity. Hence, a large portion of the wind energy is available during brief periods of high-speed winds. Okay, so also when you set up a windmill, you want to make sure you measure wind speeds and make sure that you set up a windmill right where the wind velocity is the greatest for the longest time. Okay. Now here's the deal. So as the blades are rotating, see, this is becoming, the air here is turbulent, and you don't want this blade to go into the turbulence. Then it can't extract energy. You want the blades to be rotating in clean winds. Okay. So that's where the tip speed ratio comes in. If blade spins too slow, then most of the wind will pass by the rotor without extracting energy. So if the blades are rotating too slow, all the wind is blowing by and you're leaving that money on the table. Okay, you're not extracting. If you turn too fast, then you're going through turbulence and then you're wasting your efforts. You can't extract energy. If the blades spin too fast, then each blade will always be traveling through turbulence of the blade in front of it and not capture energy. So you have to rotate at an optimal speed. Okay? It's important that just enough time lapses between two blades traveling through the same location so that new unused wind enters this location. For this reason, the tip speed ratio is the most relevant parameter in determining the efficiency of a turbine. Okay, so the tip speed ratio, which is the speed of the tip to the speed of the wind, that's the relevant ratio. Okay. So the advantages: wind turbines have a short construction time. Okay. You want to build a new Hoover Dam. How many years do you think it'll take to build a Hoover Dam?
10 years?
10, 15 years? You want to put up a Hoover Dam worth of windmills, you can do it in less than a year, 6 months. Okay. And it costs a lot less. Yep. So, and they have short construction time and small compared to other types of utility size generators. A 10 megawatt wind farm, so 100 times this would be 1,000 megawatts is a Hoover Dam. Okay. A 10 megawatt wind farm can be easily built in 2 months. A larger 50 megawatt wind farm can be built in 6 months. Now here's another thing. Wind complements solar energy well. Days with little sunshine are usually days of better than average wind. Okay, so wind and solar complement each other. Okay. So in the future, what is going to be the ideal, what is going to be happening in the future, let's say 50 years from now? The world will be running on wind, solar, what else? What else do you need? Huh?
Water?
What else do you need? Nuclear. What else do you need? What else will you need? And batteries. Okay. Why do you need batteries? Huh?
Store the energy?
At night time. Okay. So, okay. So wind, solar, nuclear, and batteries. So this, and see, none of these guys. What is the main thing? None of these guys emit carbon dioxide. Okay. So you can run the world on green energy. Okay. So this is the axis. So here, this is a horizontal axis windmill. This is a vertical axis windmill. Okay. These guys are more stable. Okay. And they're, this thing, the generator box, is on the ground level. So these guys are easier to maintain. Okay. And then, you know, no matter which way the wind is blowing, they'll rotate. So they have that huge advantage over this guy. Okay, there the generator is in there, and you know, you have to turn this to the direction of the wind and so on. And when you want to maintain this thing, you have to climb up there. So these guys are harder to maintain. But this is the windmill that you see. Have you ever seen this kind of stuff? No. So they install all these guys, all the windmills are these guys. Why is that?
Is it more cost efficient?
Okay, so with these guys, okay, the higher you go, the faster the wind is blowing. Closer to the ground, there's friction from the ground, so the wind doesn't pick up enough speed. So the higher you go, the greater the wind speed.
And with this model, it makes it like,
Right. So that's why you're willing to go to that trouble. Okay. And remember, if you double the wind speed, by what factor does the power increase?
8.
8 2 cube. Okay. So that's why you're willing to do this. Okay. So vertical axis rotors have advantages that they do not have to turn with changing wind direction. Their generator and gearbox are mounted on the ground, which reduces maintenance cost. However, they're difficult to put up on a tower to take advantage of higher wind speeds, so they're not popular. Okay. Look at this. This box, that's called the nacelle. Okay, that's where all the generator is. Okay, how big that is. Okay, and this is not the biggest these days. Okay, so that's how big that is. Okay, shown is a modern horizontal axis turbine. Such wind turbines have 2 to 3 megawatt capacity. So this windmill can run 3 homes. That's what that is. Okay. The electric generator, along with the associated drive systems and the gearbox to match the rotational speed of the wind turbine, are contained in the housing. This is called the nacelle. Are contained in the nacelle. Okay, so here's inside the nacelle. Okay. The rotor rotates at the same speed as the blades. Okay, so if the blades are going at 20 RPM, that's also going at 20 RPM. Okay. Then you use gears. Okay. So this is about in a large scale turbine. This typically is 20 RPM. So this is rotating at 20 RPM. 20 RPM. The low speed shaft is connected to a gearbox. The gearbox increases the rotational speed of the shaft to 1500 RPM. So with this gearbox, increases the rotational speed of that to 1500 RPM. This is the required speed by which most generators to produce acceptable levels of power. So you're rotating that shaft at 1500 RPM. So this wire is being rotated at 1500 RPM, okay, to produce the electricity. The generators in the wind turbines produce AC current. Okay. Now this is very important. So here's this windmill. The electricity it's producing, where is it going? It's being,
Oh.
it's being fed to the grid. Where is this guy electricity going? They're all feeding it to the grid. Okay, so let's say this windmill was in Palm Coast, this guy is in Jacksonville, and so on. Okay, the wind velocities are different. They're all rotating at different speed. Okay. Now, when this guy feeds his electricity to the grid and this guy feeds his electricity to the grid, okay, if the power in the grid is like this, the voltage in the grid is like this, when you feed electricity to the grid, you got to match that waveform. The one in Palm Coast has to do that. What does the one in Jacksonville has to do that? Exactly the same thing. What does the one in Arizona have to do?
Same thing.
Exactly the same thing. Everybody's got to match it. It's like every power plant in the country has to be in lockstep. All the winds are blowing at a different rate and all that kind of stuff. So how do you do that? Okay, so here's what we do. So the generators in the wind turbine produce AC electricity. Some turbines convert this AC electricity to DC electricity, okay, with a rectifier, and then back to AC using a rectifier. Okay, so what happens is, let's say this is the grid. In the grid, what is coming is 60 cycles. Okay, that means there are 60 waveforms every second. Okay, so let's say when you're rotating 1500 times, you're producing this waveform, you can't feed this here. So what you do is you convert this AC signal to a DC signal and then back to a 60 cycle signal. Okay? So that's what you do. So Hoover Dam has to do that. A nuclear power plant has to do that. Every windmill has to do that, and all that. Okay? Just to make sure you feed your signal in lockstep. Okay, so that's an important process. So by converting the variable speed AC current produced by the generator to DC current and then back to AC, the electrical signal is converted to match the phase meaning you're matching the shape and the frequency of the grid. Yeah. So, by the way, so that's a big balancing act, and in the grid, you're producing as much electricity as is being used. Okay, so you have to match exactly the same thing. So if somebody goes and turns off the light here, now you're using less electricity overall, so that much less electricity has to be produced. Okay, okay. So this shows you that the power in the wind goes as the speed cube of the wind. Okay, so what this is showing you is, okay, so let's imagine this is a piece of wind, okay, and that's traveling at speed v. The energy contained in it is 1/2 mv squared. This is kinetic energy, and this mass, that's the mass of this much wind, and that's equal to the density of air times the volume of the air. Okay, and the amount of time it takes for this to pass, to travel this distance, is d over v. Okay, so power is this energy divided by time, and this is the expression you get. So the power is proportional to the wind's speed cubed. Okay, you double the wind speed and the power increases by a factor of 8. Okay, so that's important to remember. Power goes as wind speed cube. The power per unit area is proportional to the speed cube. Power per unit area is proportional to the speed cube. Okay. When wind speed doubles, the power available increases by a factor of 8. Okay. So when you're putting wind farms, you want to make sure you're putting them where the wind blows the hardest and for the longest time. Since the power output from a windmill is strongly dependent on wind velocity, choosing the appropriate site is extremely important. Okay. Wind velocity increases with height as friction between moving air and ground is eliminated. Hence, it's desirable that the support tower be as tall as possible. All right, so with height, you get nice steady wind and so on. Did you guys ever hear about, so Google, what they were trying to do was they were trying to fly kites at a high place, kites, okay, and these were tethered by cables and stuff like that. And they were trying to fly these kites at, I don't remember, maybe 1,500 meters or so, okay, and produce electricity that way. So wind speed and elevation, look at this. So this is wind speed and this is the height. So this is in meters, 800 meters. That's where you get the strongest and steadiest wind. 800 meters is the tallest buildings in Daytona are about 50 meters. So about 15 times that height. Okay, so you go to the beach and the tallest thing is about 1,500 meters. 18. You guys have seen those Embry-Riddle planes fly on the beach, near the beach. They're flying at about 800 meters. Yeah. So that's how high you want to be for the strongest wind. Now we don't build towers that high. the towers that are built are about 200 meters, something like that, the tallest one. We'll see. Okay. So wind speed increases substantially with increasing altitude, and thus locating the turbine at the top of a tall tower is advantageous. Okay. However, there is a trade-off between power output and the cost and serviceability of a unit. So you want to make the tower as high as possible, but then you have to keep in mind the other costs. So they measure these wind speeds at different heights during different times of the year. Okay. So Betts's limit. Okay. So the fraction of energy. So what is the windmill doing? Okay. So here's wind blowing, and the windmill is extracting energy from the blowing air. And once the air passes the windmill, see, it's slowed down. And that difference in energy is what was extracted. Okay. The question is, how much of the energy can you extract? So the fraction of the energy extracted as a function of the ratio of the air velocity after passing through the wind turbine, V0, to the air velocity before the wind turbine is shown in the graph. So this velocity is V, this is velocity V0. Okay. And V0 to V, so this is slower than that. Okay. And you can see that, and these numbers are less than 1. Okay. So rotor efficiency, your efficiency is the highest at 59. The highest efficiency is 59%, and that's the Betts limit. Okay. And so the speed is about 40% the initial speed. Okay. The figure shows that the maximum efficiency that can be achieved in the wind turbine is 59%. This is referred to the Betts limit. So you've extracted 59% of the energy. Okay, that's the upper efficiency, upper limit. Okay. These are efficiencies of different wind turbines. Okay. So this is a vertical rotor. This is a 3-blade. This is a 2-blade. A 2-blade can be more efficient, power coefficient, except that this is unstable. This is a single blade rotor, and that's very unstable. You always see the 3-blade windmill because that's the most stable. Okay, so that's why you see the best actual efficiencies are for high-speed 2-blade design. Okay, and they're about 45%. But this guy's, the efficiency of this guy is about 40%. This guy is about 45%. But you don't see that because those are unstable. Okay? The modern 3-blade wind turbine is slightly less efficient at about 42%. The 2-blade wind turbines are prone to gyroscopic precession. Okay? You've seen a top spinning, and then it precesses. Okay, so the 2-blade turbines precess, resulting in wobbling. The wobbling creates stability issues, causing parts to wear down faster. So this guy wears down faster. His lifetime is not as big as this. Any number of blades greater than 3 would create greater wind resistance, making them less efficient. So for these reasons, for stability and efficiency reasons, so for stability plus efficiency, 3 blades are the best combination. Turbines designed with 3 blades are the ideal compromise between high yield, energy yield and stability and durability of the turbine. Okay. Cut in and cut out speed. Okay, so if the wind is too slow, then you don't want to run the windmill because you're just wearing down the parts and you're not extracting enough energy. So you don't start it till this speed. And if the wind is too high, you don't want to run your windmill during hurricanes and stuff like that. Okay, so they set an upper limit for the windmill to run. If the winds are blowing too hard, then you just apply the brakes. Okay. Below cut-in speed, the wind turbine is inefficient and produces little power. From the cut-in speed to the top rated speed, the turbine efficiency is well described by the V-cube expression. Above the rated speed, there's a risk of damage to the blades. Okay, and so you shut it down. So you measure the wind speed distribution. Okay, so here's what this is the probability. So this is for any location, and for different locations you have different graphs. So you measure this thing. So if you want to set up a windmill, let's say west of Daytona, you measure the wind speed and over time, okay, and you would measure this probability. So you see, you can get very high speed winds, but you get that with low probability and so on. Okay. So a company will measure this distribution, and this is called the Weibull distribution. So this is a mathematical, so it closely follows the Weibull distribution, which provides a good approximation to many measured wind speed distributions. Okay, so many measured wind speed distributions follow the Weibull distribution. Such a distribution is described by two parameters: the Weibull scale parameter, which is closely related to the mean wind speed, okay, so somewhere there, and the shape parameter, which tells you the shape, okay, which is the measure of the width of the distribution. Okay, so the maximum energy is extracted at high wind speeds, okay, and high speeds, this is the amount of hours, okay, so you are getting high wind speed for fewer hours, but that's when the maximum energy is extracted, okay. Because power is related to cube of the speed, the peak energy distribution occurs at higher speeds than the peak in speed distribution, okay, so peak energy is here, not there, okay. The greatest portion of energy is produced in a relatively small fraction of time when the wind velocity is well above the average, okay. So the most energy is extracted for us for a few hours during the day, okay.
Doctor's appointment.
Okay, I'm going to finish this chapter today because I want to make sure we see hydrogen. Do you know what hydrogen does? What is hydrogen? Have you guys seen a hydrogen car?
Hydrogen what?
Have you guys seen a hydrogen car?
Hydrogen car, no.
Okay. So the idea is the following. Okay. You can use electricity and split water. Okay. So and split water into hydrogen and oxygen. So the energy here got stored in here. So this is fuel. And then you can use hydrogen and combine it with oxygen in a fuel cell. And you get water plus energy, electricity. Do you guys see anything nice about it?
Is there carbon?
There is no carbon. Clean source. So you get electricity. From where are you going to get the electricity? Solar and wind. Okay. And split water. This is called electrolysis. Store this energy in hydrogen. So there can be your cheap battery. Okay. So that's a way to store energy. You produce hydrogen, and when can you use this hydrogen? Anytime you want. You can use it 3 months later. Okay. Right now, it's a little expensive, but it's going to get cheaper. Okay. So we're going to talk about hydrogen. The Artemis rocket used liquid hydrogen as its fuel, and it was burning it with oxygen to get its energy. Okay. All right, so we'll talk about that. Okay, so we build wind farms, and here's the deal. So, what do you want? You don't want turbulent air to be flowing through this windmill, so you won't be extracting energy. So that's what. So you saw this picture. Okay, so you don't want turbulent air to be flowing through that second windmill. Okay, so the placing and all the wind farm, all the windmills have to be placed strategically. Okay, so there's a okay, so here's the diameter of the blade. This guy should be about 10 diameters behind him, and this guy should be about 5 diameters next to him. So that's the placement. So shown is the optimal spacing of turbines in wind farms. Okay. Out west, in the Midwest, a lot of farmers have been putting windmills in their farms. Okay. So the land is being used for dual purposes. Okay. See, this is the wind speed, and this is more than 10 miles per hour. Okay. No, wind speed of meters per second.
Isn't that also like Tornado Alley?
I'm sorry?
Isn't that also Tornado Alley?
Yeah. Okay. So the data shown as average wind speed at 100-meter hub height. So 100-meter hub. So 100 meters is twice the height of any of the condos on the beach. Okay, and that's the height of a modern windmill. Okay, so in the United States, the most viable wind sources are along the Atlantic and the Pacific coast. So you want to build wind farms offshore. Yeah. So onshore wind turbines, wind capacity is 2 to 3 megawatts. Okay, so this is in the future. We hope to build see, the hub height is 130 meters. Right now it's about 100 meters. Okay. Offshore wind turbines, look at that. The power is 3 times greater. And so if this cost is twice this cost, you're still going to build this. You're getting 3 times the power. Okay. Wind is stronger offshore than on land. Thus, placing wind turbines a few kilometers offshore can provide substantially more energy, 50%, up to 50% more energy. Offshore windmills are currently placed in depths of about 50 meters. 50 meters depth is, again, like I said, the tallest condominium on the beach. So that's how deep the water is. Okay. Offshore wind farms are more expensive to build and maintain. Foundation work and protection from the corrosive influence of salt spray make these units a little more expensive. They have the advantage of higher wind speed and less turbulence. Okay. So that's why. Okay. So here's a 12 megawatt windmill. Okay, and it's almost as big as the Eiffel Tower. The best way to harness more wind energy at the cheapest price is to build bigger turbines. Okay, so they've already built this. Some 100 miles off the coast of northeast England, the world's largest wind turbine will start generating electricity. It's already in function. The first phase of the Dogger Bank offshore wind farm uses a turbine that stands 260 meters high. Yeah. It's taller than this guy. From the surface of the sea to the highest point of the blade. Oh, okay. So till there, that's 260 meters. Okay. Capacity factor. How long is your $5 billion invested in the power plant working? A nuclear power plant works 95% of the time. Natural gas works 50, on the average, 50% of the time, 55% of the time. Coal, 50%. A windmill works 35% of the time. Why is it only working 35% of the time?
Because it's not always wind,
I'm sorry?
because it's not always wind.
Yeah, the wind is not blowing. Whenever the wind is not blowing, it's not blowing. Okay? And the solar works about 25% of the time. On land, windmill capacity factors range from 0.26 to 0.52 depending on the location. In US, the average windmill capacity is 35%. Okay. Offshore winds are generally stronger and steadier than on land. The capacity factors are higher. Okay. On average, floating offshore wind technologies could greatly expand generation potential, as 58% of the total wind resources in the US lie in depths greater than 60 meters. So if you go to deeper side of the ocean, building that tower might be expensive, so building floating flat windmills might be the way to go. Okay. The environmental effect of wind power are almost insignificant. Okay, so the environmental, and oftentimes people quote that windmills kill birds. Look at this graph. This is amazing. Okay, cats kill more birds. So cats kill about 2.5 billion birds annually. Okay, so annual estimated bird mortality from selected anthropogenic causes in the US, 2.5 billion. Collisions with building glass. So in my office, I hear birds collide with my window every once in a while. So that's about 600 million.
What's the top one?
What?
What's the really big one there?
That's cats.
Cats?
Yeah, killing birds.
Oh, so what? Oh, okay, I see.
That's 2.5 billion. Collisions with glass buildings, 600 million. Look at this. Wind turbines, collision with land-based wind turbines, nothing. So windmills really don't.
And it's per year? Yeah,
Yeah, per year.
it's not much actually.
Yeah. All right. So what the windmill is doing is extract the kinetic energy associated with moving air is related to the cube of its velocity. Wind turbines extract this energy. Okay. So and what is the goal of the windmill? To turn this wire in between the magnets. Okay. All right. So Denmark, Spain, and Germany have the greatest wind installed capacity per capita, but China has the largest wind capacity installed, cumulative wind capacity. Okay. China is big on wind and solar.